Yeah, all right. Okay, cool. All right, bom dia, everybody. Oh, beautiful. It's so nice to be back at this lovely event. I'm Stefan. I'm usually known for all the web stuff that I do. I have done a lot of web development in the past, writing a couple books on TypeScript, and web development is also what brought me here 9 years ago to Porto Tech Hub 2016. Anybody who was at the event 9 years ago? Amazing, nobody, cool. You were? Amazing, yeah. So it was a lovely event. I have so many fond memories of the event, of Porto, the city, of the community. So I think it's an incredible endeavor that you all gathered together to create this organization and do events all around the city, culminating in this beautiful conference. Again, very fond memories, very fond memories. But you know, a lot of things have changed in the past decade, and I actually exited web development a couple of years ago, and I had the privilege of working for the last 5 to 6 years with a relatively new and upcoming programming language called Rust. Anybody in here who develops Rust? Okay, a couple. Okay, let's get this straight already. Who in here develops mostly in Java? Okay, C++. Okay. Oh, I'm so sorry, but no. I'm going to complain about every programming language today, so don't worry. Go, for the matter. Yeah, a couple of Go folks. Great. TypeScript folks. Cool. Great. Oh, very audience. That's fantastic. So I did a lot of Rust in the last years, and it's kind of great because I started out in systems programming. So I'm now 43, and back in, let's say, 2006 or so, I developed a lot of C++. I don't think I was particularly good at writing C++, but back in the day, C++ was the only choice when you wanted to have high-performance software and absolute control of what your software does. And C++, funny enough, for being basically the only choice, has gotten a lot of pushback and criticism ever since its inception. Which is interesting because C++ started out to be a very humble and reasonable project. Here's Bjarne Strustrup back in 1994. He's the inventor of C++, and this is from an interview he did for a university in 1994. Bjarne said that his main motivation for C++ was to have user-defined types, strong static type checking, and the way to be expressive for large-scale programming, also to define relationships between user-defined types. And you know, I did TypeScript for a lot of the time, and to me this sounds very reasonable. It makes a lot of sense. Every bullet point here is a strong case, even decades later. I really recommend watching this video. It's a much younger Bjarne, much more humble Bjarne, talking at length about some really good design decisions around the quirks of C. And if you know C's type system, you will understand what Bjarne actually wanted to achieve. And this is a type system joke, not a garbage collection joke. I'm coming to the garbage collection jokes later on. So again, it's reasonable. Doing C++ from that perspective was a reasonable project. But still, why is it that almost every decade, all 13 to 15 years, someone tries to replace C++ for something more modern? Take Java, for instance. So we have a couple of Java developers here in the audience. And Java is also, in terms of programming languages, a pretty old language that comes from the frustration of C++ memory management. In an interview with James Gosling, he said that the team originally considered C++ for this one particular project that they have been working on, which was software for embedded devices. And this is a little bit of irony here, but they had to work with limited resources, and this is why they invented Java. And so thinking back, it's kind of ridiculous. But the problem was that, you know, manual memory management was a problem, and they invented Java not because of the language, which was back in the day, if you squint a little bit, tilt your head, it kind of looked like C++. They even called it C++, ++, minus, which is a fun name, said that it didn't catch on. But it was invented for the garbage collection. So they wanted to have automatic memory management. They wanted to get rid of all the frustration that C++ memory management brought along, especially when working on those limited resources. Also a very interesting talk by James Gosling here. And this is why Java was invented. And now it has become what we know today. Same with Go, 15 years later. Also the Go people, this is Rob Pike, one of the inventors of Go, states frustration with C++ memory management is one of the main reasons to invent Go. Also they had to deal with really, really slow builds and uncontrolled dependencies because, you know, C++ didn't have a module system back in the day. You had those header files that you include, still to this day. And Rob Pike said, I need to look it up, give me a second. For this one project they've been working on, every binary contained about 2,000 files that simply concatenated together totaled 4.2 megabytes. And by the time all includes have been expanded, over 8 gigabytes were delivered to the input of the compiler. That's 2,000 bytes overhead for every C++ source byte, just by the way how they structured their application. So as you can tell, builds were slow, especially on local development machines. It was almost impossible to build a Google C++ binary. They even invented a build system for that. Anybody of you who started working with Bazel? Yeah, couple? Yeah. Bazel was the reason, Bazel was the answer for working with those slow C++ builds back in 2003, 2004. So this was a problem. No way of structuring your application right. And everybody in there worked with language subsets. So instead of taking the entire language, they worked on a language subset, which also led to poor program understanding. Lots of people were coming in, had a different view on the language of C++, and were writing in their style, working with a different subset than the colleagues were doing it. So reasons for inventing Go. And you can really see, if you ever worked with Go, you can really see the traces of those experiences, because Go has a very, very reduced language set, not that many keywords, not that expressive, very script-like. You know, they even said they wanted to have the feeling of developing with Python, but compiling it down to a fast binary. Which also leads me to Rust. So Rust comes from a very similar standpoint. This is Nico Matsakis. He's not the creator of Rust, but one of the main designers. And it was created at Mozilla, also for the reason that they weren't able to rewrite big parts of Firefox for the browser without severe overhead and lots of legacy in the C++ code base. And they wanted to have a programming language that was fast, delivered fast results without garbage collection. So it was one of the few programming languages back then who said, we don't want to have garbage collection, after Java introduced it for everybody, but still no compromise on performance. And they focused a lot on automatic memory management without garbage collection and zero-cost abstractions to create a very expressive language. Also a great talk by Nico Matsakis that I urge you to check out. So yeah, this was why every language designer created their own language to battle C++. But if you think about it, if you look at C++ nowadays, lots of the things that they wanted to tackle, those other programming languages, are now in C++. C++ can be memory safe. We have structs like unique pointers, shared pointers, move semantic. That's all in the language of C++. With things like concepts and type traits, you have zero-cost abstractions that are not unlike to traits in Rust. And they're also a part of the standard. We have modules and imports, finally, which should make for faster builds. A new expanded standard library with new arrays, new vector types that are aligned with the new concepts that we introduced. And also there's primitives for concurrency. Yes, they are called co_return and co_wait, and they are ugly to read, but they exist. They are part of the language. So C++ has evolved. And C++ has been Bjarne has been working on C++ longer than I exist. so there is evolution in that language, we now have all the features that we want from other language, don't we? So why are we still trying to move away? And Bjarne is also advocating for teaching a new and updated C++ instead of the old stuff. And this is true. So if I go to the university where I studied 25 years ago, they still teach the same C++ that I learned 25 years ago, which is vastly different. But yeah, to be honest, they're also learning now Rust because I teach Rust at my local university, which is great. But yeah, Bjarne is right. So we should teach a new C++. And I wanted, so why, if we have all that new stuff, why do we still want to move away from C++? And it wasn't until I heard the talk by Chandler Carruth from Google again, Google creating the next C++ successor, which is Carbon. So they announced Carbon a couple of years ago, which a vastly different approach in creating a new language. Because one thing that Chandler Carruth wants to do to replace or succeed C++ is to work for full compatibility with C++. Actually, Carbon is a new front-end language for the same C++ infrastructure, and that's the big difference. A subset, a different set, with all those move semantics, all those memory safety features included, but not with every feature included from C++. Because what Chandler said, and this is very, very true, it's not about what C++ can do now, but it's what about it could do in the past. And all the technical debt that we accumulated over decades. And it's true that we still use software, even in modern binaries that we write in C++, that is decades old and comes with all that legacy and all the troubles that we also had decades ago. If you look at the page count of the C++ standard, you can see what I mean. So on the left side is C++ where I've been working with C++. You know, it's roughly 1,000 pages of specifications in C++ 98 and 03. And the number of content has doubled in the last 20 years. To put it in the words of, I'm going to butcher the name, I'm very sorry, Antoine de Saint-Exupéry, which is the author of The Little Prince, which you might know. Perfection is achieved not when there's nothing more to add, but when there's nothing left to take away. And I know this is very hard to understand for people who invented the Francesinha. But if I want to put it in other words, it's not about what we can add to C++ to make it more like modern language, but it's about what we can't remove. Because that old stuff is still here and can still be used and will be used. Furthermore, the way that C++ is designed, it will eventually lead to adding more on top of what is, kind of alien to the language that it originally was. If you look at this house in Innsbruck, you see that the top doesn't fit to the rest of this building. And the more you look at this house, actually, the worse it gets. And also, you have more than one way to do things. This is also in Innsbruck. It's fantastic. And maybe there's a little gatekeeping joke hidden in there somewhere. And this is not exclusive to C++. This is actually something that we see in JavaScript and ECMAScript as well. We are adding more stuff to the language without asking if we really should do it. And stuff that is not visibly compatible with the language as it was. All right, this is the setup. Let's talk about Rust. I want to be fair. I want to have new features in a programming language. I want to have a programming language that can move along with my programming needs as time progresses. Because even if Venkat said that he wants to get rid of all programmers, it's still fun. I love programming, and I want to have a programming language that can accompany me throughout the next years. Stopping at the design and calling it perfect is actually what Go tried to do, and I don't know if they succeeded. So they made this one version 1.0, and then they spent 15 years in trying to integrate generics where you still argue if it was even necessary or not. So yeah, I want to add new stuff to a programming language. It's okay to add new stuff to a programming language, but I want to have it in a stable way. And I think from my experience with Rust, I think that Rust found an excellent way to create a solid baseline that allows for innovation for a programming language. And the answer is in its second core pillar, abstraction without overhead, which is basically the name for traits. So if you didn't do any Rust, I tried to make it as easy for you as possible. It's going to be a lot of syntax that you're going to read now, but I hope I will get my point along. I try to build up from small examples to something rather big. Traits are shared behavior between types. And you programmers, you have written an interface in your life. Yeah, okay, it's what an interface is supposed to be. It's very much like an interface in object-oriented languages, but also much, much more powerful. And one of the key differences is that also language features are abstracted in traits. So how does a trait look like? This is an example. By me, it's slideware. It's not something that you would do in an actual project, but I guess it illustrates really, really well what a trait is. So I'm having here two structs. This is how you define a new type in Rust. And then I define a trait called billable. And this billable says, I want to have this one method, bill, that returns a floating point with 32 bits. And then I can implement this billable trait for certain types. I implement it here for maintenance hours, where I calculate the hours and the rate and get the amount that I can bill. But what's funny is, not only can I implement traits for my own types, which is what you would expect from an interface, I can also implement my traits for foreign types. Here I implement billable for F32. And now every F32 is compatible with my software that depends on billable. And this is, I guess, one of the main differences. And with that way of defining a trait and being able to implement it for every type that I can have for foreign types or for my own types, I create this relationship between types that Bjarne wanted to have. Another example. So I'm having a struct for Fibonacci numbers. It has the current value, it has the next value. And instead of just, going recursively or iteratively through all those Fibonacci numbers, I want to implement it as an iterator, where I get always the next Fibonacci number. So I implement the iterator trait, which is a trait from the standard library for Fibonacci. It wants me to define two things. One is an associated type called item, which in that case is a U128, and the next method where I can get the next item. It has an option as a return value, which basically says either I have a value or I have no value. If I have a value, you can call next. If I don't have a value, then you stop the iteration, basically. And with that, I make my Fibonacci struct compatible with everything that accepts iterator, even for loops. And here I implement the default for Fibonacci, so if I don't know how to construct a new Fibonacci struct, I just call default, and I have a default instance of it. How do I use it? So here I create a new Fibonacci struct, and then I just iterate through it in a for loop. The cool thing is, with implementing this iterator trait, Rust as a language knows that it can be used in for loops. So if you have a vector, if you have an array, if you have anything that is iterable, it can be used in for loops. And my structs as well, because I defined the iterator trait for this particular struct. If I don't know how to create a new struct, I just call default. And then I get all the Fibonacci numbers for this particular range of memory. Also very interesting, I can use all the existing interface methods. Obviously, this is what I want to have from an expression like that. Here I create the new Fibonacci struct, take 10 and collect them into a vector. And this is all glued together by just defining this one iterator trait for the Fibonacci struct. I can do all those things just like they're supposed to. Funny thing is, this is actually evaluated at compile time, so it's not running at runtime to pick out those 10 numbers from the Fibonacci iterator. It actually evaluates it at compile time and has the result in the binary afterwards, which is quite nice. I took the iterator trait from the standard library and implemented it for my struct. What I can also do is take trait implementations from a third-party library and extend the already existing 72 iterator methods with, 115 more iterator methods. Which is the great thing, if you can implement traits for other types, I can create a library where I say, I want to implement those methods for everything that already implements iterator. And with that, all those methods become available for every iterator that already exists and will exist in the future. So I make my struct Fibonacci already compatible with everything from the itertools library just by defining this one little piece impleterator for Fibonacci. Again, it's about those relationships between those types, making it possible to extend my software in such a way. And everything of that is, of course, compatible with a for loop. Talking about the for loop is a language feature. I have here another example. I'm having here a struct clock. It stores hours and minutes. I implement basically the body of the struct, where I say I can create a new one. I can normalize it so the clock doesn't go beyond 24 hours and the minutes don't go beyond 60 minutes. And I have also a way to add more minutes to it. But this actually is not something that I really like in that way. Why would I want to have an add minutes method if I can implement the add trait for clock? So in the top part, I implement the add trait for clock. It requires me to implement or to define two things. First of all, what should be the output? In the upper example, the output is another clock, which means I can add one clock to the other and get another clock. And this is what I do in the implementation of add. I just take both. I take myself and the one right-hand side clock that I get in for an addition and add the two of them together. Now I can add two things of the same type. Here in the second part, I can also specify the same trait implementation for a different type. I say I want to add U32 to another clock and can define the output to be clock, which means now I can add any number in the U32 range to my existing clock by just using the plus operator. And this might look like operator overloading a little bit, that you know from C++, but it's still a little bit different. So while it functionally might do the same, because you're able to use the plus operator, I have a single concept in there, which is the trait, which allows me to do that. And with generics and the associated types, I have much, much more possibility to create more add implementations for this particular struct that I'm defining here. So here I already defined two different addition possibilities for my clock. I even can flip it around. I can say implement standard ops add clock for U32, and now you can flip it around. Now it becomes associative. You can flip the clock and the U32 from right-hand side to left-hand side. And it still works. So I have much, much more fine-grained control about what I can do there. And again, it's about defining those relationships between those types. You can ignore the part at the bottom. It's basically just printing it out so it becomes beautiful on your command line. All right. So with that, you might ask, okay, if I can implement traits and if I can define traits and can implement them for my types, for other types, and if I can take trait implementations from libraries that change how my types behave, isn't there a lot of room for collisions? Yes, there is. This is why there is one set of rules that you need to follow if you want to implement traits. First, you can implement your traits for your types. This is what I showed you with billable. That's easy. Then I can implement foreign traits for my types. This is like the iterator, like the add trait, etc. I can implement my traits for foreign types. This is how I implemented billable for F32. I'm not allowed to implement add again for U32 if there's no type from my world involved. So while I can do impl add clock for U32, it has my type clock involved. I cannot implement U32 for I32 or for another U32. This is not possible. I either need to own the trait or I need to own the type to make that possible. Cool. Again, it's about relationships between types. And with that, with establishing those little rules, I also have access to programming paradigms that exist for I don't know how many years, and everybody always says don't inherit, composite your types. It's much, much better. And in Rust, it actually becomes the one single way to do that if you want to build up on existing features. Rust doesn't have object-oriented notion of inheritance, deriving classes from a parent class. This is not in the language. Thankfully so. We need to find other ways of doing things like that. And one thing is composition. So here I'm having a vector with a couple of URLs. And I want to sort those URLs. To sort them, I create a new binary heap and push all my URLs into that binary heap. But if I print them on the command line, they're actually sorted alphabetically. And I want to sort them by the length of the string. So while I can use it, it doesn't work. So how am I able to get the URLs that you can see here in URL : parse to work with the binary heap, but have functionality that is to my liking? And usually in object-oriented programming languages, I would derive from UL, my own class, and override this one functionality that compares different URLs with each other. Since I can't derive, I need to create my own struct. So here I create a new struct called shortest first. It includes the original struct. This is actually, this is the composition part. You can see it in the syntax directly. I have shortest first, and inside there's the original struct that I want to composite. And then I implement the order trait for my new struct. I implement partial ord for shortest first, and then I do all the comparisons with each other. And the comparison here in the ord implementation, I get both parts, see how long they are, and then I compare the left one with the right one. And then it's ordered by length and not alphabetically. The ord trait requires partial ord to, no. I guess the equal trait requires partial ord to work. And for partial ord to work, I need to have the ord trait implemented, if I'm not mistaken. One thing that is very interesting if you look at that, so it might look like a little bit of overhead to do that as compared to just deriving from an existing class. But it becomes incredibly obvious what this shorted first UL should do, because I don't look at the implementation, I don't look at what's actually being compared, I just look at the traits that I implement for this particular type anymore. This is also when you see that you have some information leaking. If you derive a class from another one, you have also all the access to the parent class features, even if you don't want them. This can't happen here because the struct shortest first has nothing attached to it, as long as I don't do it. And what did I attach to it? Exactly what's in those traits. And I know exactly with what it's being compatible after I do that. And this is one of the key features of Rust for me. Not only am I very expressive in defining what I can do, it becomes also a very readable language through that. I can look back at that code and understand what's going on. And I'm the proof of that because I looked at the code just yesterday when I put out this one particular slide for this presentation that I created a year ago. But it becomes obvious what's happening in there. And then I compose. So instead of just adding a URL parse into the binary heap, I wrap it in this shortest first struct, and now the new functionality kicks in. More traits, also necessary for error handling. So you heard about the $1 billion mistake from Tony Hoare, where he said, okay, you know what would be cool for algo 60? Null pointers. And ever since he said, okay, he thinks that this decision to include null pointers in algorithm 60 has created $1 billion of errors. So I think it's much, much more. I've been to those meetings where you, every day, every morning at 9 a.m., you have 12 people looking at the screen, looking at the null pointers, and everybody who raises their hand gets the bug attached to their team. So I think it's much, much more than just 1 billion, but it exists. Rust does not have null pointers, which is funny. You know, JavaScript has 2 of them, null and undefined. Rust does not have null pointers. They have enums where you can have either one or the other, which means that if you do error handling, it can get very verbose. So I'm having here a read number from file function where I say, okay, I open the file, and if the file does not exist or anything else, then I need to return an error. Otherwise, I return the file. Then I create a new string buffer where I want to read my contents into it. Either this works, but if it doesn't work, then return another error where, you know, say that you can't read the file. Then I want to convert it to a number. What if it isn't a number? Then I also need to somehow return an error if this doesn't work out. And while the function signature is very nice to read because it has a U32 or a string, it's either I get the U32 as a result or I get a string as an error. Those are the 2 things that can happen here. The implementation itself for just reading a number from a file and parsing it into U32, it's very verbose. But I can implement traits from my own struct to make that go away. And I do just that. So instead of working with all those details, I say, I want to create my own error type. It's called number from file error. It can be 2 things. It can be a parse int error if I can't parse the number, or it's an IO error if the file is not there, or if I can't read the file, or if the string buffer doesn't have enough room, whatever. I need to implement 3 traits for it. One is the debug trait, which is an auto implementation. It says derive debug. Now the debug trait is implemented for my struct. Or I implement the display trait for a number from file error, where I present the error in a string. That's all it does. And all the error trait needs is to have a way to show what error actually happened. That's all the error trait needs. And then I implement the error trait. And with that error trait, it becomes hooked into the language. So now it's not only that I say that I expressed myself through all the structs, but I can make use of features from the language, and I'm going to show you in a second. Next to those traits, I also implement conversion traits. So I say, okay, I want to go from a parse int error, which happens when I parse the number, for file error, so I can convert it here. And I also can implement IO error to my new number from file error, the same way. And with all those traits in place, I can reduce the code that I had before to this. So instead of constantly checking for errors, I just say, I want to open that file. If it doesn't work, look at the question mark operator here. Bubble up the error. Standardfs file.open can produce an IO error, but I can convert my IO error into a number from file error because I implemented those traits. And now I can bubble it up. Same with read to string into the string buffer. It can produce an IO error, and I can bubble it up. And same with the parsing error. This can produce a parse int error. If it happens, just bubble it up. I even have numbers here. Look at that. So this is where I convert the IO error into a parse number from file error. And this is where I convert my parse int error into a number from file error. And the code becomes very, very dense. So it's golden path programming. You just see what you're actually interested in. But I don't hide anything. I don't hide a thing because I see that errors can happen. I can see it from the result type in the method signature. I can see it from the question mark operator. I don't hide a thing. It's still visible what's happening and where errors can happen. It's just that I focus on the stuff that interests me and I have everything that is related to error handling somewhere else. Again, a very readable language. Funny thing, error traits existed way before the question mark operator. So this is how Rust implements new features. They define a trait. They try for the whole ecosystem to converge to the trait. And then they add the language features for making it more comfortable to work with. Okay, I need to look at the time. I have until 12, I guess. So a bigger example. This one is really, really heavy. But not only, right until now, I just showed you how I use standard traits from the Rust standard library, from my own types, to make everything compatible with each other. So I have this one relation to the standard library and to everything that Rust offers me by implementing their traits. But I can also use traits. Sorry. I wasn't sure if something falls down or if it's just music. But I can also use traits to not only hook into the standard library, but to glue the standard library and other libraries together. So I'm having here, don't focus too much on those details. It's a lot of code. It's a store for images. So I'm having a store where I can put images in and get images out for a web service. So everything that I do here is just getting an image via a URL from some store. But I implemented, and this is now important, I implemented another feature, and this is a lot. I implemented another feature to get a grayscale version of those images. And there's a lot going on, because first I check if the image even exists. If it exists, fine. If not, I'm returning a forbidden error, because if I don't have an image, I can't create a grayscale image. If I have an image, I create a dynamic image type through this image library. So this is a library from Crates.io that I pull in. It creates the dynamic image type, and here I take all those bytes and create this dynamic image library. All right. Once I have this image, so this happens in the first 10 lines. It's a lot. Once I have this image, I create a new vector. I have a cursor to the first byte in this vector, and then I go through the image, create the grayscale implementation, and write it into the new vector. This is happening here. And once I have the grayscale representation in this new vector, I create those bytes and pull them back here as a response. There's a lot going on. I have this image create, I have the web framework that I use, I have my own types in a database, which is here a key value store, so not the best database. And parsing this is a lot. I mean, it's still possible. Rust is a very expressive language, you can read it. But it's still a lot to parse. It's 20 lines of code for some very mundane functionality. And I want to get rid of that. I want to make it easier. Again, through the power of traits. So I take this particular line down there. I want to focus on creating those image responses. Because here there's lots of details that leak into my code. Strings, mostly strings and bytes and whatnot. And actually what I want to focus more on is an actual image response type. A type that contains the bytes that I want to represent as a result. I implement a new constructor, not a lot, and then I implement the into response trait from this web framework for my type, where I put in all the details. I create content time image VMK, those bytes, whatever, all those details. And now I talk about different things. I don't talk about all the strings anymore. I talk about image responses that come from bytes. I finally have a noun attached to what I want to do. And then I want to go from a dynamic image, which comes from the image library, to my image response. Again, from this one foreign type to my type by using a trait from the standard library. And this almost reads like English. Try to go from a dynamic image to an image response. I implement it twice, once depending on which ownership rules that I currently have, a totally different topic. Here I implement it for the reference. And here is the whole creation of a new vector with the new cursor and writing it to that particular array. This is happening here in those 4 lines. Once for the owned image and once for a reference. This can error. It's try from, not from, so this can be something that errors. And I created my own error, KV error. And I implement go from image error to a KV error as well. I have all those status handling. If this is not possible, if I can't convert this particular image to an image response. So instead of all those lines that we had at the bottom, everything we had, this vector handling and the cursor and whatnot, it becomes this single line. Here I get the image. I work on that in a second. And here I just say, create an image response from the grayscale version of that image. Look how easy this is to read. And look, there's even information that an error can happen through the question mark operator. And it reads like English. Go, try to create an image response from the grayscale image. I don't talk about dynamic image. I don't talk about the into response trait or whatever. I don't talk about the content type. I don't talk about PNGs, nothing. This is what I want to do. All the abstractions, all the details are abstracted away into those trait implementations. And I can work with nouns and verbs that actually make sense. And all just by using traits as this binding thing between relationships. I think that's beautiful, honestly. This is why writing Rust is so much fun, because I can go back to that stuff and understand what's going on. Real quick, just for completeness sake, don't worry. Here I create a new store type that can store dynamic images. Then I create a function where I get it out of the database or where I can put it in. And if I have that abstracted as well by changing that type, this is the grayscale function. Because I abstracted the entire reading of the database also into its own thing, into its own type. And then I get the image out and say create an image response from that image. So instead of those 20 lines, I now can look at 4 lines and understand what's going on. This is actually the example that excites me most about the whole thing. All right, real quick. There's also transitive trait implementations, which is actually quite nice. So here I'm having an app state. An app state has a database. The database can be a hash map of a string key and a string bytes tuple. Whatever. I also have I want to use that app state and put it into a read-write lock and then into an atomic reference counter. This is a lot of asynchronous and concurrency details that I don't want to bore you with. But you need those structs to be able to share that state around threads. I don't want to create the new app state. Then I want to create a new RW lock, then a new atomic reference counter. I rather want to say shared state : default. And this works because arc, RW lock, and my app state all implement the default trait. So because they all implement the default trait, I can pierce down to the very core of this nested generic type that I have and just say share state : default. Also one of those convenient features that helps if you rely on traits that make the programming language. I left out a lot of things. So this is mostly connecting your types to language features by using traits, but there's also things like reflexive traits. If you implement from for a type, you also get the into trait implemented, so you can do different conversions between types. Or if you have the display trait implemented, you can also call to string because it's a different trait, but it's also auto-implemented. One thing that is also very interesting if you think about the language features, I spoke about async. Rust does not have an async runtime. You need to add your own async runtime to it if you want to work with it. This allows Rust to be flexible for your use case, if it's embedded, if it's web or whatever. But async tasks are part of the language. And async tasks are represented through the future trait. Again, a trait that has been included into the language first. Then everybody converged towards the trait, and then they created the async and the wait features that work directly with the runtime that you attach to it, but on a language level. So it's really easy to hook into the language by implementing those traits. And you know what I did recently? I implemented my own memory allocator where I wanted to have a vector in a file. And I was able to do that because I implemented the allocator trait and used it for every vector that I had. So that I have the possibility to change memory allocation by implementing a trait for my own type is incredible. and possible through Rust. And I think with traits at the core of Rust, we finally have achieved what Bjarne actually wanted to do when he created C++. We were able to define relationships between user-defined types. That's what traits are about. We improved static type checking. If the traits don't line up, you get some errors. And we are able to tap into language features even before they exist. Traits can be very verbose, especially if you work with a lot of associated types and lifetime bounds and whatnot, but they're also very expressive. So if you use traits, you really tell your fellow developers what's going on in your software. It's not all roses, so I have to admit, because complex traits create very complex error messages. If you ever had a future being rejected by an async runtime, you can have pages of errors, but this is being worked on, again, through another trait. Also, you might think traits are interfaces, but they are not. They work kind of differently, especially if you want to say, okay, I accept anything that is, I don't know, an into response in here. Nope, it doesn't kind of work that way. You need to use a trait bound. You need to use a specific keyword. So you need to get used to that. And trait discovery still can be a problem in some cases. So knowing which traits to implement requires experience, unfortunately. And for me, this meant when discovering Rust, I actually came because of the performance and memory safety. It was necessary for the project. But I stayed for the expressiveness of the type system. If you understand traits, you will be able to dip into every Rust project and understand it. Talked about all those conclusion items already. I just want to close with, with the Antoine de Saint-Exupéry quote, it's not about what we can add to C++, but what we can't remove. And let's talk again about perfection. Because perfection is achieved not when there's nothing more to add, but when there's nothing left to take away. And maybe there's nothing left to take away from a Francesinha. Maybe it eats another side of fries. And this is just, so maybe Francesinha is perfect as it is. Just like traits. They do a lot, they are very expressive, they are very verbose at times, but they are the single, and dare I say, perfect concept that allows us to create a stable future for Rust, for the Rust programming languages without compromises. Thank you very much. I guess we still have some time for questions. So, so if you want to leave because you're hungry or you want to have refreshment or whatever, I don't mind. But if you want to chat with me a little bit about Rust, I'm still here.